Hello all, I am Dr. M. Shanti from Department of Physics, Kamaraj College of Engineering and Technology, Virudhunagar. In this video, we discuss about the particle in a one-dimensional box. The particle in a one-dimensional box is the application of Schroedinger wave equation. To start with our today's topic, one should have clear idea regarding quantum physics, wave function psi, and Schroedinger time dependent and independent wave equations. The link has been given in the description box. Kindly check it for the clear basic idea about the quantum physics. Now let's move on to our today's topic, particle in a one-dimensional box. So consider a one-dimensional box. Consider a potential box with one dimension and its length is L. Inside the box, the potential energy is 0, and outside the box and at the walls of the box, the potential energy is infinity. Here in our system, we take an electron of mass m. The particle, that is the electron of mass m, is confined inside the one-dimensional potential box. The electron is confined in the one-dimensional potential box. The electron is in the one-dimensional potential box. Inside the potential box, the energy, potential energy V is equal to 0, and at the walls of the potential box, the potential energy is infinity, and outside the box also the potential energy is infinity. So the electron inside the box cannot penetrate through the walls of the one-dimensional potential box. Since the walls and outside of the potential box is having infinite potential energy, the electron is confined within the potential box itself, so that the potential box sometimes termed as potential well. In some textbook and web pages, the potential box, one-dimensional potential box, is referred as one-dimensional potential well. That means the electron is confined or trapped within the one-dimensional potential box or well, and it cannot escape through the walls of the one-dimensional potential well or box. Okay, good. Then we write the boundary conditions in the simple mathematical forms as, that is, V of x is equal to 0, V of, here the potential, here in the potential box, the length of the box is L. When the x value is greater than 0 and less than L, the potential energy is 0. That is, inside the box, the potential energy is 0. V of x is equal to 0 when x is greater than 0 and less than L. And another boundary condition, that V of x is equal to infinity. The boundary conditions are written in the simple mathematical expressions like this. Now we have to apply these conditions in the Schroedinger one-dimensional wave equation. Already we have discussed that the particle in a one-dimensional box is the one of the application of Schroedinger wave equation, so that we are applying these conditions in the Schroedinger one-dimensional time independent wave equation. We know that the Schroedinger time independent one-dimensional wave equation is dou square psi by dou x square plus 2m by h cross square e minus v into psi is equal to 0. Here the psi is the wave function. The psi is the wave function. Here it denotes the wave function of the electron. The E is the energy of the electron and V is the potential energy. And we have written one more new term, H cross. H cross is H by 2 pi. H cross is H by 2 pi. This is the Schroedinger one-dimensional time independent wave equation. In our case, in our system, the electron is moving inside the box. So inside the box, the electron has no potential energy. So V is equal to 0 inside the potential box. We are substituting V is equal to 0. The potential energy is equal to 0 in the Schroedinger time independent one-dimensional wave equation. Hence, the equation is reduced as d square psi by dx square plus 2m by h cross square into E psi is equal to 0. This is taken as equation number 1. For simplification, we have replaced this term by k square. So, we obtained the equation number 2. The equation number 2 is the second degree differential equation. The second degree differential equation is that d square psi by dx square plus k square into E psi is equal to 0. Now, we have to find the solution of this second degree differential equation and it is directly given. The solution of the second degree differential equation is given by psi of x is equal to a sin kx plus b cos kx. The psi of x is the wave function of the particle in the one-dimensional box. This equation have two constant a and b, the arbitrary constant. Now we have to evaluate the constants a and b. For that, now apply the boundary conditions of the one-dimensional box. First, the first boundary condition is at x is equal to 0, the potential energy is infinity. At the first boundary, x is equal to 0, the starting point of the one-dimensional box at x is 0 and its potential energy at the wall is infinity. So now we apply the first boundary condition, x is equal to 0 and the potential energy is equal to infinity in the wave function equation, the solution equation. It becomes sin kx, a sin k, instead of x I am substituting 0 plus v cos 0. At the walls of the one-dimensional potential box, the probability of finding the particle, finding the electron is 0. At the walls of the one-dimensional box, the particle is not present. So, the wave function is not exist at the walls of the potential box. Hence, psi of x is equal to 0 in this case. So, on substituting all these values, we get 0 is equal to a sin 0 plus b cos 0. Now, we get the arbitrary constant b is 0. It is obtained by applying the first boundary condition in the solution of the second degree differential equation. Now we are applying the second boundary condition to the solution of second degree differential equation. The second boundary is that the starting point of the one-dimensional box is x is equal to 0 and the ending point is x is equal to L. So, the second boundary is that x is equal to L. At the second boundary also, the potential energy is infinity. Hence, I am writing the second boundary is x is equal to L and the potential energy V is equal to infinity. At the boundaries and outside the boundary, the particle does not exist. So, the wave function becomes 0. The wave function of the particle does not exist in the outside of the box and at the walls of the box. Hence, the wave function is 0. Psi of x is equal to 0. Now, I am applying all the boundary conditions in the solution of the second degree differential equation. Now, consider this term. In this term, A cannot be equal to 0 because the constant, both the constant A and B will not be 0 in the given case. Both the constant is 0 means then the whole term, then the whole wave expression will become 0 and no particle will exist and no wave function also exist. So that the second constant A is not equal to 0. But this equation implies A sin KL is equal to 0. Hence, we assumed that A is not equal to 0, but the sin KL must be equal to 0. If A is not equal to 0 means another term sin KL automatically it should be take the value 0. Sin KL is equal to 0. Whenever the sin value becomes 0, sin 0, 0, sin pi 0, sin 2 pi 0, sin 3 pi 0, it goes on. Sin n pi is equal to 0. We know that the sin n pi is equal to 0. Hence, in this term, if it is replaced by np, then the sin 0 value will be the resultant. In this equation, if we replace instead of KL the n pi value, then we get sin n pi or the sin KL is equal to 0. So, I am rewriting this as sin n pi is equal to 0, where L is equal to n pi. Here I have replaced the KL term. Instead of this KL term, I am replacing the n pi. Hence, I have written KL is equal to n pi. The K value can be rewritten as K is equal to n pi by L. The K is the wave vector. The K is the wave vector, and already in the previous case we have derived the K square value. Now, we have calculated by assuming the constant value as the K value n pi by L. Now, we are going to equate these two equations. Already we have derived the K square value. The K value just now we have derived. K is equal to n pi by L. This K is squared on both sides. Then we get K square is equal to n square pi square by L square. These two equations represents the same K square value. So, I am equating these two equations. Equating these two equations, we write 2me by h cross square is equal to n square pi square by L square. We want to find out the energy value of the particle in the one dimensional box. Hence, I am rewriting this equation as E is equal to n square pi square divided by 2m into h cross square. I am rewriting the equation and obtained E value as n square pi square h cross square by 2m. We know that h cross square is, that is h cross is equal to h pi 2 pi. Then h cross square is equal to h square by 4 pi square. Here substitute the value of h square, then n square pi square, n square pi square. Instead of h cross square, I am writing h square by 4 pi square into 2 into m. Pi square cancelled. On further simplification, the e value is n square h square divided by 8m L square. On equating these two equations, I am writing 2m e by h cross square is equal to n square h square by L square. I want to find out the energy value of the particle in the one dimensional box. Then on rewriting the equation, I write E is equal to n square pi square into h cross square divided by 2m L square. Instead of h cross square, I am substituting the value of h. The h cross square is equal to h square by 4 pi square. So this equation becomes n square pi square h square divided by 4 pi square into 2 into m L square. On cancelling the pi square value, we get the equation as n square h square by 8m L square. Finally, we obtained the energy value. Finally, we obtained the energy of the particle in the one dimensional box, that is E is equal to n square h square divided by 8m L square. This is the energy of the particle in the one dimensional box. This energy value is termed as eigenvalue. The energy value, that is the energy of the particle in the one dimensional box, is called as eigenvalue. Already we have derived the arbitrary constant b value as 0. Now we have obtained the constant a value as root of 2 by L. Now substitute these two constant values in the equation of the wave function of the particle in the one dimensional box. On substituting, we will get the wave function as psi is equal to a sin n pi x by L. Instead of a, I am writing root of 2 by L. This is the wave function of the particle in the one dimensional box. The energy value is the eigenvalue. The energy value is corresponding to this wave equation. Then on substituting 1, 2, 3, on substituting the values for n, we get the wave equation, the wave as the like this in the diagram. The diagram represents the energy value of the particle in the one dimensional box when we substitute the values of n as 1, 2, 3, etc. This is the sample for the energy value up to 3. Thus, we have obtained the wave equation for the particle in the one dimensional box and its energy eigenvalue. Thank you for watching the video. Thank you.